Hi, welcome back. And this is a second lesson. And after taking a look at some things, we're going to change some things around a little bit. And I'll kind of explain that as we go along. But I want to just remind you, we left off with order of magnitude estimating. Okay, and so you should have already done that worksheet and taken a look at that and have a rough idea of how we can use this. Now, it might not be something you use every day, all the time, but again, it's a good skill to have. Now, in our class, we're going to be doing a lot of labs. In those labs, we're going to be taking measurements. And basically, a measurement is describing the world around us and comparing it to some known values. Okay? And so it's a way that we use to do this and then explain to somebody, like you have a rough idea. And I'll give you an example. If you tell somebody that you're traveling in your car at 30 miles an hour, everybody has a rough idea of how fast that is. If you tell somebody you're doing 70 miles an hour, like, oh, okay, that's significantly faster. So by having this measurement, something to compare it to, it gives us an idea of what's going on. Now, we have to remember that no measurement is exact. There's always going to be some uncertainty. Because mathematics, which is always exact, is the language of physics, we have to take great care into trying to keep that uncertainty as small as possible. So we have to take great care when we're doing our labs to try and eliminate the errors as much as possible. Now, we're going to be dealing with something called significant figures. Now, you should remember some of this from chemistry, a little bit maybe from physics, but basically it's a way to know the number of reliably known digits in a measurement and the subsequent calculations from that measurement. Okay? Now, because our measuring tools are not extremely precise, especially in this class, we have to take into account the error that's introduced every time we take a measurement. Now, when doing those calculations, those errors can become compounded. Okay, and I'll give you an example. If I want to know the area of this particular object, okay, and let's say I can find out its length, but let's say I only know it to the nearest centimeter. So 1.12 centimeters when I do that. And if I measure this one right here, and I get this to be let's say it's not going to be very close to thing. Let's go 1.46 meters. And I should have meters. Let me change that other one back from centimeters to meters. Come on, erase, baby. There we go. Into meters. Okay? And so there's my length and my width. Now, I would go ahead and calculate out what the area would be by taking the length times the width. And so when I do that, I would get area, which is length times width. So the 1.12 meters times the 1.46 meters. And what that's going to do is when I calculate that out, I get an area of 1.6352 meters squared. Now, this 5.2 on the end of this, that implies that we know this down to the 10th of a millimeter, okay, or the 10,000th of a meter. But because our measurements weren't that accurate, these two digits are basically meaningless. And so by using sig figs, we're going to know that our answer is not alluding to the fact that we're more precise or less uncertain than what we actually are. So what you need to remember is when we calculate out. Now, the good news is when I taught you this in Regents, I told you, hey, sig figs don't matter because really they're not going to count against you in the Regents. In AP, they will. You need to have some respect for them. Now, does it have to be exact? No, this isn't going to be as precise like we're trying to calculate, landing on the moon or something like that, or landing on Mars. So it have to be exact, but you have to have some rough idea. So you can't write out all 10 digits that your calculator spits out, okay? And likewise, you can't round a number down to the nearest 100 either, okay? So basically what you need to do is you need to follow these rules. And again, I'll help you out with this. We'll approach this as the year goes on and continue to work on this. But remember that when you're adding or subtracting, okay, the number of places after the decimal in your answer must be equal to the least number of decimal places in your original numbers. Okay, and there's a worksheet we're going to be working on this here in a little bit. So if I go 1.23 and I want to add on 2.4, if I add those together, I'm going to get 3.63. But this last 3 isn't significant because I only have one place after my decimal in this particular number, so I can only have 1 after this one. Now, if I'm multiplying or dividing, in this instance, the number of sig figs in your answer must be equal to the least number of sig figs in your original numbers. So if I were to do the exact same numbers, so the 1.23 times the 2.4, if I were to multiply those, I would get 2.952. But because this only has 2 significant digits, I have to have 2 significant digits on here. So this actually becomes now 3.0 because this 9 is going to be rounded up by the 5. And so my answer would end up being 3.0, implying only the 2 significant digits. Now, percent error and percent deviation. Because we're concerned with how exact our measurements are going to be, we're going to be finding out percent error and percent deviation. Now, they're very, very similar. Percent error is if you have a known quantity and you want to compare your result or your answer to that known quantity. Percent deviation is when you don't necessarily know the correct answer, but what we'll do is we'll take a class average and we'll say, hey, this is what the class got as a whole. How far are you away from that class average? Or we're going to assume that this answer should be this. How far off are you from there? Now, it's going to be very, very simple, and I just want you to write this down, because if you don't know this one, you're definitely going to be using it a fair amount. So I want to make sure you have it written down somewhere. So if you're doing percentage error, it will be your actual minus your experimental. Take the absolute value of that. So we're just going to drop the negative. And then we will divide that by the actual, and then multiply it by 100. Similarly, if we're looking for percent deviation, so percent dev, instead of the actual, we'll do the accepted, which I'll put as ACC, minus the experimental, divided by my accepted. Again, don't forget, sorry, my fault on that. You need to make sure you take the absolute value of this and times 100. And so you'll know it's basically the exact same thing. One's going to be the actual number, so we actually know what the answer is. And the other one is going to be what we're accepting is a close enough result, and we're going to find out how far off you are from that. All right, at this point in time, I'm going to skip over the vectors piece and slide all the way down to the very last slide. Only because vectors is going to take some time, and I don't want to make this video 40 minutes long. Okay, so I'd rather spend some time. The very last slide, and this is something I just added on this year because this is something that we really need to get better at, okay? Graphs. Graphs are the bane of our existence. They always have been in Regents, and they're going to be it probably again, but we will continue to work on this. Now, throughout the year, you'll see just like in Regents, primarily we're going to use equations, okay? But data, especially ones that we get from our laboratory activities, can often be interpreted, and you can extrapolate that data from and see the trend that that data is showing from tables and graphs. You're going to be able to going to have to remember the key relationships, as well as being able to do something called linearizing the data. Okay? And so what I mean by that is that if you have a graph that looks like this, you know that that is a direct relationship. And as such, one of the things that we always did last year is that we would find the slope of that graph. Now, if you don't remember this, I'll put it down. This is something you should definitely have in your head somewhere. The slope, remember, is equal to rise over run, or the change in y over the change in x. Okay, y2 minus y1 over x2 minus x1. But you want to find the slope. And so if you have this direct relationship, you're going to be able to find that slope. Now, a few of the graphs are going to be doing will look like this. Okay, remember last year we called this an exponential. I'm changing it up. We're going to call that a power this year. Okay, this is what we referred to before, is that y is equal to x squared. Okay, that kind of implies that. And so Normally, we would try and do a fit on this, but we wouldn't necessarily get the greatest answer on this. So what we would do, normally this would be y and this would be x, and this kind of relationship shows y equals x squared. Now, we're going to do something weird initially, and then we'll continue to work on it so it makes more sense. But we're going to linearize the data, meaning we want to graph something that will show us a direct relationship. And so what we're going to do is we're going to take, and since we assume this is y equals x squared, we will take and we will graph y and x squared. So rather than y equals x, which shows us that power, this will show us y equals x squared, and this theoretically should give us that direct relationship again. And once we find that direct relationship, we once again can find the slope. And so when you find the slope, that will equal y is equal to something times x squared. And this right here will be your slope. And that'll tell you by how much it's going to change. And so there's a worksheet on this, and I'll show you that here in a second since I changed my 2. It doesn't want to erase. There we go. I've got to get better at writing 2s. But if you go into your stuff, and again, I'll jump into Emma's really quick. If you take a look at your graphical methods, okay, there's a nice reading on this graphical methods, how we graph stuff, okay, what the different graphs show. It tells you the curve, how to find that curve fitting, how to find out what the y-intercept is, what it means, and those kind of things, along with how to linearize the data. So I'm going to end this video here. Take a look at this, and then there are 4 things. If you look at the practice, there are 4, oops, those are the key relationships. There are 4 that I would like you to graph, okay? And after you graph it, then linearize that data after you do that. Okay, so take a look at that. The other thing I'd like you to do too on this is look at the ratio word problems. This is something I want you to have done before we come into class, okay? And it's just a matter of solving problems that you don't necessarily know how to do. So it's kind of a critical thinking skill. See what you can do, see what you can find. And we'll go over this when we come into class. So try this today as well. And so we're going to end there, and I'll have one more video on vectors, and we'll be done with the summer assignment. Have a great day.